Hi everyone, I'm Maria Cristina Bisi from the University of Bologna. Today I'm going to talk to you about using wearable sensors for the monitoring of locomotor development in preterm children. Thanks to advances in medical care, number of preterm infants is increasing more and more worldwide. One of the most frequent issues encountered by preterm children is an increased risk of motor difficulties, ranging from mild impairments to cerebral palsy, with prevalence 3 to 4 times greater than in general population. In particular, the knowledge regarding the non-cerebral palsy motor impairments is still limited, although affecting up to 50% of children born at less than 30 weeks of gestation. Clearly, the early and timely identification of mild motor difficulties would be crucial to implement effective interventions. So the aim of the present study was to develop a sensor-based solution for the quantitative monitoring of motor trajectory in preterm children, supporting the identification of early biomarkers of motor impairments in this population. 3 groups of 2-year-old toddlers matched for age and walking experience participated in the study. A group of preterm children considered at high risk of motor delay, that is, born at less than 28 gestational weeks or with a body weight lower than 1,000 grams. A group of preterm children at moderate risk, that is, born between the 28th and the 36th gestational week, and a group of full-term peers considered at low risk. Children walked at self-selected speed in a corridor, wearing 3 inertial sensors on the lower back and on the shanks. For each participant, 14 strides were considered. Normalized stride time, stance, and double support duration, symmetry, and short and long-term variability were obtained from the mediolateral angular velocity of the shanks. Nonlinear metrics of trunk kinematics, that is, multi-scale entropy and recurrent quantification analysis, were calculated on the 3 trunk acceleration components. Between groups differences were analyzed with respect to risk of motor delay using a Kruskal-Wallis test. A significant effect of risk of motor delay was shown for normalized stride time, stance, and double support duration, short-term variability, sample entropy on the frontal plane, and for recurrent quantification analysis only for one parameter, determinism, calculated on the mediolateral component. In this figure, you can see median and interquartile values of the estimated parameters represented on a polar plot for each group. By looking at the upper left quadrant, you can see that temporal parameters decrease with decreasing risk of motor delay. The same trend can be observed for short and long-term variability in the third and fourth quadrants, respectively. Finally, in the first quadrant, we can observe that, with decreasing risk of motor delay, there is an increase in motor complexity on the frontal plane, which is assessed by multi-scale entropy. In conclusion, sensor-based gait analysis allows differentiating gait performance of toddlers at different risk of motor delay. When analyzing the present results with respect to the expected trajectory of locomotor development, children born preterm, in particular those at a higher risk of motor delay, exhibited a less mature motor control performance during gait, characterized by lower stability, longer support phases, and higher variability, although this higher variability was not structured toward the exploration of more complex movement, and this is highlighted by the lower multi-scale entropy values. The proposed set of parameters can serve as biomarkers for the early detection of the risk to develop persistent motor impairments in preterm children. Thank you very much for your attention.